Hello, everyone. Thanks very much for sticking around for my talk. Today I want to talk about contracts, testing, undefined behavior, and how to turn it into well-defined behavior, and how all of those things kind of interconnect and what you can learn from them about how we think about C++. So this whole conversation is kind of happening in a context of kind of backdrop of this topic of safety. Right? This has been a pretty hot topic in our industry and in the C++ community in particular over the last year or so. As there's a big push from government agencies for the whole industry to shift kind of away from memory unsafe languages like C and C++ and to embrace memory-safe languages like Rust and C#, et cetera. So it caused quite a stir in our community, and quite a few people said, this is an existential threat to C++, and we need to do something. So pretty much every other conference I went to this year had a heavy focus on safety. There were lots of talks given about this. So at CSS Now in May earlier this year, there was a keynote by Chandler Carruth about safety. There was a keynote from JF Bastian about safety. There was just a couple weeks ago at CppNorth in Folkestone, UK, there was a keynote by Sean Parent about safety. They're all really great talks. I encourage you to check them out. Want to mention a couple others. Andreas had a great talk about how to actually develop safety critical software from the perspective of somebody who actually does that. And then I actually did a talk here 2 days ago about C++ and safety from a perspective of somebody who doesn't do that, kind of a bit more of an outside perspective, and kind of gave my take on this whole topic. And that talk is kind of in some ways a bit of a prequel to our talk today. So if you're watching this talk later on YouTube, I encourage you to watch that one first, but please do not watch the version that I recorded at the C++ Stockholm meetup, because that was a very rough kind of rehearsal version. There were lots of mistakes in there. Don't watch that. Watch the version from CppNorth. And one thing that kind of, I guess all of these talks, among many other things, are trying to do is to establish a common terminology, right? So that when we talk about safety and security and correctness, all of these terms that are kind of flying around, we agree on what they actually mean. Because sometimes people use these words and they mean very different things when they say them. So it's kind of good to agree on that. And this is what all of these other talks are about. And it turns out that, it's useful to qualify these things, right? You can talk about functional safety, that's a property of a system. And then, when you talk about C++ in particular, this other thing comes up a lot, which is language safety. And this is how I call it anyway. And you can consider a program language safe if it exhibits no undefined behavior. Right? I think this is a really useful definition. This is a definition of safety that a bunch of other people have used. So I think this is helpful when you talk about C++. And we can also take this to the kind of programming language level. Right? You can say that a language is safe if it is impossible to express a program in that language that has undefined behavior. Right? And so under that definition, Rust is a safe language, whereas C++ isn't. Right? And you can break this down further. Memory safety kind of consists of at least type safety, bound safety, lifetime safety, initialization safety. We talked a lot about all of these things also on CppCast over the last few months. Then there's thread safety. There is arithmetic safety, that your arithmetic operations don't have UB. There's definition safety, which is something that is talked about maybe a little bit less, but I think it's important, especially in the context of C++, because it turns out C++ out of the box doesn't have any of these safeties, right? So you can easily subvert the type system by doing type punning and reinterpret casts and all of these evil tricks, which are typically always UB, and I have a talk about that I did a bunch of years ago. Bound safety, you don't have that. Nothing prevents you from indexing into a vector or an array with an out-of-bounds index. Lifetime safety, we have use after free, dangling pointers, references, invalid iterators, like you store an iterator and then you push back into a vector, it like reallocates everything and then you have an iterator pointing nowhere. All that kind of stuff, this is where all of these security vulnerabilities come from, right? And then we also don't have arithmetic safety, right? Signed integer overflow is UB. We don't have thread safety. It's very easy to end up with a race condition or other bad things. And when it comes to definition safety, you maybe have experienced this like very unfortunate situation that you end up in if you, for example, have a definition of a struct in one translation unit and then a slightly different definition of the same struct in a different translation unit. And you link it all together in the same program, and then you have like really, really weird bugs that are very difficult to track down because that's an ODR violation, and in the standard we call this IFNDR, ill-formed, no diagnostic required, which is very bad, and we have a lot of IFNDR in the standard. And so this whole discussion focuses a lot on all of these things are UB, how can we make them not UB, it's bad that they're UB. And yeah, those are important discussions, but I think before we do that, we actually have to answer a different question, kind of step back and ask ourselves, what actually is UB? Right? What is undefined behavior? I think that's a non-trivial question, right? And so I hope we can all agree in this room that undefined behavior is always a bug. Like, I hope nobody would disagree with that. But it's also really important to recognize that undefined behavior is also not an error, right? So it's not that your compiler goes ahead and says, ha, you did something that you're not allowed to do. So, instead of telling you that, I'm going to punish you by inserting some instructions that are going to erase your hard drive, right? This is not what UB is, right? UB is when a compiler makes certain assumptions, when it compiles your code, and then it optimizes your program based on those assumptions. And then you violate those assumptions. There's a bunch of talks given on this topic, which I also recommend you check out. They're both great, and there's others as well. And then you violate those assumptions that your compiler already made when it compiled and optimized your program, and then you get what you get, right? So here's an example. This is from a blog post by Ram and Chen. We have an int array here, right, table, and then we have a very simple function that kind of takes an int value and sees if that value is somewhere in this array. And if it is, it returns true, and otherwise it returns false. So of course there's a bug here. Who sees the bug? 4, right? Okay, so I should have written I smaller than 4. I wrote I smaller than equals 4. And so that means that if the value is not in the array, I'm going to be indexing into this table with I equals 4, which is an out-of-bounds access, which is undefined behavior. So what is this going to do? Well, sometimes on some compilers, you might get what you get in the sense that it's going to go into the memory that's after the array, right? So you might read some random stack memory or maybe heap memory, and this is where all of these security vulnerabilities come from, right? You're reading memory you're not supposed to read. But there's also something entirely different that might happen, right? A compiler might be really clever and might say, well, indexing into this table with I equals 4 is undefined behavior, therefore it will never happen, and I can assume it will never happen, right? And so if I can assume that I is never going to be 4, then I is also never going to be 5, right? Because in order for it to become 5, it first needs to become 4, and that can't happen. Therefore, I can never be 5. Therefore, I can never reach this line of code. Okay? Therefore, this function can never return false. And therefore, I can optimize out the whole loop and just say, return true. And so then you get this really subtle bug where you're not reading any uninitialized memory or anything like that, but you just have this function that just returns true even if the int is not actually in the array. And so, under certain circumstances, if you have a tool like a static analysis tool, you might be able to catch that if you use that tool. For example, I copy-pasted that into CLion earlier, and I wanted to see if the data flow analysis is going to find it. And yes, it did in this case, right? Because we wrote 4. This is a string, an integer literal, right? So the tool sees what you're doing there. It can see through your code. It can do analysis and say, this is out-of-bounds access. But if the 4 were a runtime value, for example, then the tool wouldn't be able to know what's going on, right? So here's another example. There's another loop here with integers. There's a multiplication here. And the compiler can assume that this will never overflow because signed integer overflow is UB, so therefore it can never happen, right? So it can then, under that assumption, kind of make an equivalent transformation and move this multiplication out of the loop because that's a good optimization, right? So it's going to actually eliminate the variable I entirely. And then it's going to say, well, this is 4 billion. This is rated on int max. Well, therefore, this is always true. And so there, you're going to get an infinite loop. So instead of printing 4 integers, you're going to be in an infinite loop, printing a lot of integers with increasingly weird values. So if you have undefined behavior, it can have all kinds of effects, right? We can have crashes, freezes, wrong data being read or written, very surprising behavior, as we just saw, code paths being optimized out of existence. We can have time travel optimizations. This is especially fun. If you want to see some examples of that, you can Google time travel optimization. And we get security vulnerabilities. So this is kind of where we are with C++, right? C++ has a lot of undefined behavior. And a lot of the time, it can be avoided with good engineering practices. Right? Unit testing would have caught like both of those bugs that we just saw, right? You can do fuzzing, you can do code reviews, you can do coding guidelines, right? Like the core guidelines or MISRA, which is what safety critical software people use. Sometimes you can diagnose the UB at compile time, like we saw if you have a static analysis tool, if it can see through your code at compile time. And sometimes if it can't, you can catch it at runtime with a sanitizer like UBSAN or ASAN and all of these great tools. But all of this has trade-offs, right? So they have a typically huge runtime overhead, so you're not going to use them in production. Sometimes you can avoid UB by just using a higher level abstraction, right? For example, mutexes it's very easy to end up with UB if you misuse mutexes, but you can wrap mutex with something like a library, like boost synchronized value, or there is the guarded object from libguarded, great library. And so if you use those tools, then you cannot get it wrong. You cannot have undefined behavior. And so a lot of the time, when we have an unsafe primitive, we have these things we can wrap around that are actually safe. And some of it, we can fix on a C++ committee by actually evolving the C++ language and taking some construct that is today UB and make it not UB in the next version of C++, right? But some of this UB we can't fix in any of these ways. Like these tools are not going to find it, and we can't really change the semantics there. So what options do we have then? Well, we could rewrite everything in Rust. This is, for some companies, is going to be like a viable and very good option, right, to solve the problem. But for some people, it won't be, because you can't afford to rewrite everything in Rust, or you don't want to, write Rust, or you just have all of this legacy code that you depend on, and it's just like prohibitively expensive to rewrite it in Rust, or it doesn't make sense. And so we're kind of stuck with C++, right? Because we have to support all of this legacy C and C++ code that we depend on. And so then the next question is, well, why can't we just fix it all in C++ itself? Right? Why can't we make C++ a safe language? And I talked about this in a lot more detail on Monday. But basically, yes, theoretically we can, because obviously, Rust, for example, or Val, or other programming languages are languages that don't have UB, so it's clearly possible. So we could take C++ and evolve it to be a language like that. We could theoretically do this. But like with everything in engineering, there are trade-offs involved, right? And the trade-offs here, if you prioritize safety, there's a trade-off with performance often. Rust actually gets that mostly like performance in Rust is, from what I've seen, actually pretty good. But there's a big trade-off, especially with C++ with backwards compatibility, right? We have to be backwards compatible with all the C and C++ code that we are already using today. And there's sometimes a trade-off with correctness, right? Safe code is not necessarily correct code, or it can do something wrong. Like it can be safe in the sense that there's no UB, but it can be not functionally safe in the sense that it's incorrect, it's doing something bad that can itself be a safety issue, right? There's a trade-off with complexity potentially and other trade-offs. Just to give you an example, you can not initialize a variable and then use it without initializing it. And that's UB in C++. And the language itself is not going to prevent you from doing this, right? So how can we get rid of this UB? As the C++ committee, we could decide, okay, we're just going to make this all formed, right? In the next version of C++, in CppNorth23, like this is no longer going to compile. You have to write int I equals something, right? We could do that, and that would solve the problem, right? But then a lot of code out there would break, so we can't really do that, right? And there was an idea to introduce something like epochs, where we have like different versions of the language, but there's technical problems with that approach that we don't currently know how to solve. So we can't do this. So if you're in this situation, You can use tools, right? You can, again, put this into a tool, into a static analysis tool or whatever you have. And the tools are really good. They're going to tell you, you didn't initialize a variable here. Like, that's bad. But the problem with those tools is they're all opt-in, right? You can use them, but there's nothing forcing you to use them. And so therefore, C++ as a language isn't safe. So what can we do about this? Well, for example, in this case, there is a proposal by J.F. Bastian to fix this in a different way. And by the way, I'm going to show a few papers from like the committee. And so each one of them has this paper number. And if you type in your browser w21.link/paper number, you can get to that paper, right? So that's a very easy way to look up these papers if you're interested, you want to dig a little bit deeper. And so that paper says, well, we can't make it a form, but let's just implicitly initialize, every such variable to 0, right? And so that solves the problem as well. The UB is gone. There's no breakage, right? No code breaks, right? So any code where the semantics change was actually undefined behavior before, so it's kind of strictly better, right? But there are other trade-offs, right? So one trade-off is correctness, right? Maybe 0 is actually not the correct value. Like, for example, on Unix, I believe user ID 0 is root, so that's probably not a good default value to use in that case. But you're kind of prohibiting the tool from diagnosing that. You're kind of masking the bug, right? Because the tools can't tell anymore. Did you mean to write, did you mean to initialize it to 0, or did you mean to leave it uninitialized? Like, your intent isn't clear anymore. So not only does it kind of mask potentially the bug, so there's a kind of correctness issue, but there's also an expressivity issue. Like, you can't express anymore what you mean. And there's also a performance trade-off, right? So, initializing something to 0, if that's not what you want, is kind of paying for what you don't use. And maybe with one integer on any modern platform, that's not going to be a measurable performance issue. But if you have an array of 1 million integers, that's definitely going to be a problem, right? And so, high-performance computing people are not going to want to use the language in that case. This is why, for example, they don't use stud complex, right? Because stud complex forces you to initialize everything to 0. So they're using their homegrown complex instead. By the way, they're in for a bad surprise when we standardized std in C++26, and then they find out that they can't use their custom complex with std. That's going to be interesting. But that's another story for another time. So we have to provide, people who have performance, who can't afford a performance regression, but some kind of opt-out, right? So you might introduce some kind of attribute to opt out of this, right? So this is kind of good because then, you still can do both things, but like the safe thing is now the default rather than the unsafe thing being the default. So that's good, but there's a trade-off with complexity. How would you actually specify this attribute exactly? It turns out it's really, really difficult to specify it in a way that covers all the cases. And so now we increase the complexity of the language. And there's all of these trade-offs. So now actually we have quite a few papers floating around in active discussion that kind of look at all these different trade-offs. They propose different possibilities. So it's very, very not obvious, what the right thing to do here is. So I don't know what you're going to end up doing. This is going to, I guess, keep the committee busy for a while, this topic. But yeah, there's all of these trade-offs. And so kind of my opinion here is, or my thesis here is that because we can't just always choose the left-hand side, because we have to account for all of these other things, and there's all of these trade-offs, we can never actually make C++ a fully memory-safe language. Like, this is just not going to happen. And as I said on Monday, I think we kind of just have to accept that fact. And I think that is actually fine. We can make it safer than it is today, right? We can take something that's UB, and in cases where the trade-offs are right, we can make it not UB, or we can make the safe thing the default, or we can offer, a safe way of doing something where previously there was no way of doing something that wasn't UB. And actually on the committee, like, we're doing this all the time. We've been doing this for quite a while now. Like in C++20, we got std_bitcast, which is a safe way of doing the type punning thing without UB. And then we got implicit creation of objects, where you can take a pointer to a buffer and then just cast it to struct x, and then instead of it being UB as it was before, it's just going to magically create an object of type x, and the behavior of that is defined under certain conditions, right? In CSS23, we finally fixed the range-based for loop, which had this really annoying problem. If you have on the right-hand side of the colon, you have like a temporary object, and in certain cases that would go out of scope and become dangling like before the for loop actually kicks in. So we fixed that. Thank you very much, Nico. That was a very important fix. And we keep doing this, right? So in this current release cycle for CppNorth23, we're looking at this uninitialized value stuff. JF actually has a different paper also on trivial infinite loops or infinite loops in general, which are actually also UB. An infinite loop that doesn't do any I/O or other things that are observable is UB, which I didn't know until recently. It's quite interesting. I have a paper which is kind of a bit on hold because I got stuck with a few wording issues that I don't know how to resolve, to make it not UB to read the underlying bytes of an object. That's also a problem, right? If you have an object like an int or whatever, and you can cast it to a const char, and that in itself is not UB because const char, like char star, can alias everything, but actually then doing pointer arithmetics on that is UB because there is no array, so you can't do any pointer arithmetics. So that's UB. We need to un-UB that. There's kind of more long-term stuff. There's ongoing work by Bjarne and Gabi to create a more safe C++ by introducing profiles and doing other interesting things. There's work going on introducing lifetime annotations. That's another approach to get rid of these like lifetime issues. And then there's contracts. This is a big thing that's been ongoing for a while now. And arguably, in my completely unbiased opinion, this is probably the most significant of these efforts that's going to give you the most benefit the fastest. And so let's talk about contracts. Design by contract is a term that was coined by Bert and Meyer in the 80s when he was designing the Eiffel language. And so basically it says that you should define preconditions, postconditions, and invariants for your types in a certain formal way. And then those specifications are referred to as contracts in accordance with a conceptual metaphor with the conditions and obligations of business contracts. This is kind of the rough idea. And so this is a really promising approach. And one kind of different way to like look at this is, we're talking about all of this UB, and this is UB, and that is UB, and we have to ask ourselves, what is actually UB? I think we kind of figured that out now. The next kind of logical question is, how does the UB actually get into our code, right? So how does it happen that the line of code that causes UB actually gets into our code? And why is it UB? And sometimes this is, obvious. It's like you write this, okay, you reference a null pointer, that is UB, so that line of code, just don't do that, right? So sometimes it's as simple as that. But sometimes it's actually a lot more interesting, right? So let's say we have a vector, and then we're gonna get an index from somewhere and we're gonna index into that vector, right? And then, we don't know where this index is coming from. Like the static analysis tool is not gonna be able to tell you if that's UB or not. So how do we reason about whether or not that's UB, right? So I is gonna have some value at runtime. If you just look at this code, we don't know what that's gonna be. We don't know if it's gonna be UB, right? But you can think about it in terms of contracts. So we can say that, vector operator square bracket has a precondition that I is smaller than size, right? And so then if I is 5, for example, then you violate that precondition, right? So a mathematician would say, you call a function outside of its domain. The value in this case is not defined, right? It's kind of a mathematical way of thinking about it. And so what then happens is that, if the preconditions of vector operator square bracket are not met, and you then go into vector operator square bracket, you're gonna hit UB there, right? But the interesting thing here is that the line of code, which is the actual UB, is inside of like vector.h. But the line of code that actually causes the UB, which is the call that violated the contract, is outside. It's like on the other side of an API boundary, right? And that is something that where contract is like really, really helpful to reason about this kind of UB. So some terminology. Here's a definition of a precondition. What a precondition is that I found on the internet. It says that a precondition is a condition that must be true just prior to the execution of a function or other piece of code. Well, I actually don't think this is a very useful definition in the context of C++ because it doesn't tell us what happens if the condition is violated. But it turns out the standard tells us that. So the standard has a definition of preconditions. It says, the condition that the function assumes to hold whenever it's called, and that should now sound familiar. And violation of any preconditions result in undefined behavior. Okay. And so you will find if you look in the standard that, if you have like, definition of operator square bracket, it's going to say, precondition, I smaller than size, right? It's going to say it right there in the standard. And so here's another piece of terminology. If a function has preconditions, then we say it has a narrow contract, right? So there's some combination of input values, like values for the parameter, or some other state that is accessible from the function. And if the system is in that state, then it's going to be undefined behavior to call the function. And we say that that function has a narrow contract. And as far as I can tell, this terminology is actually specific to C++. I don't know if anybody else kind of uses this terminology. And then we say that a function that doesn't have any preconditions, like it's never UB to call it, has a wide contract. Okay, so we have narrow contract, wide contract. Okay, let's do some audience participation. Let's see if we can figure out which functions have a narrow contract or a wide contract. And I'm going to use vector because you all know vector, and vector is great. Okay, so std vector size. Does it have a narrow contract or a wide contract? Wide. Okay, great. So it's never UB to call size on a vector, right? Empty, narrow or wide? Wide. Oh, you're great. Okay, so it's never UB to call empty. Operator square bracket, narrow or wide? Narrow. Okay, great. Vector at, narrow or wide? Wide, right. So you can call add out of bounds. And if you do that, it is an error. It's going to throw an exception, but it's not UB. So it's wide. Vector front, narrow or wide? Narrow. Okay, it's UB to call vector front on an empty vector. That's UB. Vector back, narrow or wide? Narrow. You're great. Reserve, narrow or wide? Wide. Okay, so reserve again can fail, right? It can throw bad log or something, but it's not undefined behavior. Vector begin, narrow or wide? Okay. so if you call vector begin on an empty vector, you're going to get an iterator back, which is a past the end iterator, right? So dereferencing that iterator is UB, but calling begin is not UB. So that's a wide contract. Vector end, narrow or wide? Wide. Okay, you got this. Okay, last one. Vector swap, narrow or wide? Ha, okay. I didn't know that's one. This is tricky. So for a normal state vector, yes, swap is never UB. But if you have a vector with a custom allocator, yes. And then the allocator threads of that allocator say that propagate on container swap : value is false. And if then the two vectors don't have the same allocator object, that's UB. Okay, so that's a narrow contract for the case of vector with a custom iterator under certain conditions. Okay. Yeah. This is what it says. Like if it's propagate on swap is true, then you're good. And regardless of that, if both vectors have the same allocator, like object, not just like type, but object, you're also good. But if both of those are not true, then it's UB. Okay, probably not something you're gonna need in everyday life unless you're using allocators, which some people do. So one more bit of terminology. If we have a function with a narrow contract and we call it with valid input and valid state, so it's not UB, we can say that this is a call in contract. If we call it with invalid input or state, we can say it's a call out of contract. And out of contract calls are UB. Right? And so you're going to see these definitions in the standard. Precondition is whatever. And so typically we specify these contracts today often in English, right? So the standard does it in English. If you have your own library, which is not the standard library, you might just document it somewhere, like put a comment, above the function. Behavior is undefined unless the vector contains at least one element. So this is how you might want to do it. So there is a specified contract, but the contract is specified in English, right? And so if you then call that function, you hit this UB, which is specified in English. But actually there is another distinction here which is useful. So the documentation says that this vector front call is UB, but we can say that it's library UB or I like to call it soft UB. Some people call it library UB. So it's UB because your library says that it's UB, right? You're violating the contract. But it's not actually language UB, which I called hard UB, because that's what happens when you actually call the function. You hit the line of code that actually has the hard language UB, like dereferencing a null pointer or indexing into an array. So we have library UB when we violate the contract, and that may or may not lead to language UB kind of on the other side of the API that you're calling, right? Often it will lead to hard UB, but not always, right? You could conceivably implement vector front in a way that if it's like an empty vector, then you, I don't know, you create a static default element and you return a reference to that one, right? So that's not UB. So that's soft UB that doesn't cause hard UB. It's not a particularly good idea to do that, in my opinion, because that's not going to be correct code, but it's going to be kind of masking the UB. So it's a way to like harden things without actually getting correct code. So soft UB does not necessarily lead to hard UB, but it often does. But here's the thing. What if you could take the soft UB and diagnose it when it happens, and then turn the soft UB into an error before the hard UB occurs? And this is exactly what contracts are about. And so, wouldn't it be great if instead of formulating the contract in English, we could actually formulate it in code? We could say, okay, vector front has a precondition. And we write that in code somehow, and the syntax is like strawman syntax. Like, it doesn't really matter at this point what the syntax is. But like, we would have some syntax to say, this function in code, this function has a precondition that the vector is empty. And then operator square bracket has a precondition that the index is smaller than size. And then we would have some kind of switch that says, well, if this switch is on, actually check if the precondition holds, and if the precondition is violated, give me an error. Don't go into that function and don't cause the hard UB. And that's going to be safe, right? So it turns out we actually do have today in standard C++ a facility that does that. Assert, exactly. It's the good old C assert. It's doing exactly that, right? So in release mode, it's doing exactly nothing, but in debug mode, if ndebug is not defined, it's going to check the predicate, like the expression inside the assert. And if that does not return true, it's going to print a diagnostic and terminate. That's a contracts facility. It's kind of a crude one. Like it does find the precondition violation. It's not particularly flexible. In lots of scenarios, termination is probably not what you want. So a lot of people and companies will then define their own assert macro, which is doing something slightly better. Who has an assert macro in their code base? Okay, that's pretty much everyone. So how would you implement this? So here's a kind of paraphrased example from an assert macro from a framework that I've spent a lot of time working on that I shall not name. So if you're in debug mode and you didn't set the flag that you disable your assertions, you're going to check the expression. And if the expression is not true, you're going to invoke some kind of violation handling mechanism, which is this stuff. I'm going to call this violation handler. And it's going to log the assertion, and then maybe it's going to do more stuff. You can do whatever you want in there. Like in this particular framework, it's doing this thing where it's checking if you're running under a debugger. And if you are running under a debugger, it's actually going to trigger a breakpoint. So this is actually something that we're hopefully going to get in CppNorth23, thanks to René Rivera over here, who wrote a paper on standardizing std breakpoint. So thank you very much, René. We very much hope you're going to get this in CppNorth23. But until then, there's like platform-specific ways of doing this. So you handled your violation, you did what you wanted to do, right? And so then the next choice you have is, do you terminate or do you keep going? Right? And so a lot of the time, you probably want to terminate because if you keep going, you're probably going to hit hard UB, right? You don't want that. But there are some cases where you do want to continue. For example, termination is not an option for you, right? There are genuine use cases where that's the case. So typically, you would have a choice. Sometimes it's a compile time switch, like in this case, it's another hash define that depends on some other flag, whether you terminate or continue. In some cases, it might be a runtime choice, right? Like the Visual Studio thing when you violate an assertion that pops up and says, oh, the assertion has fired. Do you want to like ignore or abort or whatever the options are, right? It could be a runtime choice as well. And then you could also say, well, if I disable assertions or if I'm not in debug mode or whatever other flag I'm using, I'm just going to ignore the whole thing, right? So we can call this contract semantics, right? You can say that a contract can have one of possible semantics. And one semantic is enforce. You check the predicate, and if it's not true, you handle the violation, and then you terminate. Another semantic is observe, right? You check the predicate, if it's not true, you handle the violation, and you keep going. Now, knowing that you might hit hard UB and it might not be a good thing, but maybe sometimes that's what you have to do. And then ignore means don't do anything. So these are quite frequently used. There's actually a fourth semantic, assume, which says, do not check the predicate, but tell the compiler to optimize based on the assumption that the predicate is always true, right? So you've seen this before, and the flip side of this is violating the assumption is now UB. So this is actually the opposite of safety, right? So you were saying that we don't want to turn soft UB into hard UB, you want to turn soft UB into an error before the hard UB occurs or doesn't occur later. Assume actually says, turn the soft UB into hard UB immediately. That is actually sometimes really useful if you really need to squeeze every nanosecond out of your code and you need to get certain optimizations that you wouldn't be able to get otherwise. This can improve performance if you don't care about the safety aspect of this, right? So you can get better code and better performance out of this. And so one of the kind of problems with the CppNorth20 contracts proposal was that like it wasn't really clear if it was supporting this assume semantic and how exactly that would do that. And there was kind of some disagreement between the authors of the contracts proposal whether or not like the assume semantic was handled and how. So when CppNorth20 contracts got pulled from CppNorth20, I actually went ahead and said, well, this assume semantic is really useful in certain cases where you really want this optimization for performance. So let's just extract it out. Let's make them independent. Let's get kind of assume as a separate standalone tool where we can tell the compiler, assume this expression optimized based on that and just independent of all the contract stuff. And then if you get contracts later, we can somehow integrate them later. But you want to have this like primitive, right? And so I wrote this paper, and it took me 3 years of my life to get that through the committee and figure out how to standardize that correctly, specify that correctly, and we went through 8 revisions. But we now have it in CppNorth23. Right? And so just a quick summary of how this works. Let's say you have some kind of function. This is a toy example, right? So a function that takes an integer, divides it by 32. So if you compile this in our highest optimization setting, you're going to get assembly output, this x86 anyway. This looks something like this, right? It's going to like, depending on, you have to kind of do basically signed integer division here. These are the instructions that are doing signed integer division, okay? But now you can say, well, but I know that x is never going to be negative because that is an invariant in my code. I know that, but for some reason the optimizer can't see it. Maybe it's an invariant that's established too far away from this piece of code or in another translation unit or something. There is some code that makes sure that that's the case, but the optimizer doesn't see it. And so then you can tell the optimizer, you can assume that x is never going to be negative. You can put that attribute in there. And then the generated code you get is this. The compiler is going to say, well, I don't have to deal with the case of I being negative at all, so I can throw out these instructions and just reduce the division by a bit shift, right? So yes, there's a question. Yeah, I mean, yes, it's a toy example. You could also just use an unsigned in. But there are actually examples, where, like more realistic examples like this one, where in this case, you have an array of floats. Right? This is very common, for example, in audio, where you have like just a signal. It's basically like an array of floats, right? An audio signal. And then what you want to do is you want to loop through this whole array of floats and clamp all the values in there between -1 and 1. Right, so this is very common. It's kind of a limiter. It's a very common operation in audio. It's going to be probably somewhere in a hot loop. Performance is really important. It's real-time code, right? So And often there are certain invariants about this that you know, because this is just the way your audio format works. And you know that certain properties always hold, but the optimizer doesn't see it because either these invariants are established in a different translation unit, or the code is just too far away for the optimizer to see it, or too nested for it to reason about it, or whatever. So you can just directly inject these assumptions into the code. And sometimes you just know that the array is never going to be empty. And like very common in audio, the array size is always going to be a multiple of 32, right? Like your buffer size is typically always a multiple of 32. And then if you inject those assumptions, then the optimizer can generate a much better loop for you. It can throw out like the prologue and epilogue and all of that stuff. And so then if you do the std clamp, actually you can say, well, I know that the numbers are never going to be none or infinity or something like that. And then the compiler can actually go into header, like whatever header clamp is defined, and I think it's algorithm, but it might be numeric. I think it's algorithm. I don't know. Doesn't matter. So it can go in there and throw out a bunch of code that is dealing with all of these edge cases, right? So you get much better code gen. And sometimes you get actually performance optimizations as well. It's going to be faster. And sometimes the performance optimizations you get and the kind of speed up you get, there's literally no other way to get them, because it's things that the optimizer will never be able to reason about unless you tell them. Of course, this is super dangerous, right? If you get this wrong, and if you pass in an array that is size 17, then things go horribly wrong, and you have horrible UBA. But people who would care about every nanosecond, sometimes it's useful. There are cases, genuine cases, where this gives you performance improvement that is very significant. And so we might take our debug macro here and kind of add this new flag here, assume my assertions, and then say, okay, assert is now actually going to be turned into an assumption. Well, of course, assume is a brand new feature. It's only supported, as far as I know, by GCC 13 at the moment. So if you want to actually use this in production, you have to wrap it into another macro. And then this is how this other macro looks, right? So it's always like this, right? We know this. This is kind of what we have to do because it's C++, so it needs to be painful. If your compiler supports the attribute, you're going to use the attribute. If it doesn't, then you fall back to, depending on the compiler, like certain compiler intrinsics that essentially do the same thing, because this feature has been around for a very long time in the form of these compiler intrinsics. And then, if you're not on one of those compilers, you can fall back to like increasingly, unlikely to actually give you the desired effect, like workarounds. The last resort here is I'm dereferencing a null pointer, which is actually an interesting case of dereferencing a null pointer in production code. This is like a genuine use case for doing that. But that aside, so you can do that. The question whether, that's actually a good idea has been looked at by various people. They come to very different conclusions. There was a paper by Herb a few years ago where they took the MSVC compiler itself and they just turned all these assertions into assumptions, and they just saw what happens. The first thing they saw is that they got lots of crashes that they didn't get before, because people were actually not using assertions to check invariants, but like for kind of defensive coding. They were like checking things that were not necessarily true, and then if you turn them into assumptions, very bad things happen. And then when they get rid of that, they actually saw that turning all the kind of assertions into assumptions actually slowed down the code rather than speeding it up. So that was interesting. But then there's another paper by the Bloomberg people, and they found that in certain cases you get a very significant speed up, right? And so this is kind of consistent with what I saw. So I always kind of wanted to do my own benchmark to look at this properly myself. I never got around to do that yet, but I do want to do that in my copious spare time. So yes, there is this assume semantic, and occasionally it is useful. But like most of the time, you need enforce, ignore, and sometimes observe. So there are these contract semantics. Another axis here is contract kinds. Right? We talked about preconditions. There's also postconditions, which is kind of the flip side of that. Right? It's something that the function guarantees when it returns. There's assertions, which is something like in the middle of your code, right? And there's class invariants. So preconditions and postconditions are properties of a function interface. Assertions are properties of a function implementation, so they're typically an implementation detail. And there's class invariants, which is a property of a class interface. And so facility for programming with contracts in C++ should be able to do all of these things, right? It should support all the 4 possible contract semantics. It should support preconditions, postconditions, assertions, and invariants. And it should support custom violation handling. And it turns out that if you do this today with like macros and all that stuff, you can get most of it, but the only contract kind that we can express is assertions, right? Because you can't put annotations on kind of directly on a declaration of a function or declaration of a class without language support. It's kind of fine because if you have a precondition, it's actually equivalent to an assertion, which is the first thing like inside the body of the function, right? Excuse me. And if you look into like your code base where you have assertions, you're going to see that very often, an assertion is actually the first thing in the function body. And whenever you see that, that assertion is actually a precondition check. And sometimes the assertion is not in the first line of the function body, but it's somewhere in the middle, but it's kind of at the start of a block inside the function. And that typically is a little bit of a code smell. It means that that block actually is a function that you should maybe factor out, and then that assert is the precondition of that inner function. Okay, so we have postconditions as well. So this is something, as I said, that the function guarantees about the state of the program when it returns. So we can look at vector again. There's pushback. Pushback has a bunch of postconditions. Right? Can you name a postconditions of pushback? What's a postcondition of pushback? Sorry? Right, so somebody said it. So one postcondition is that back is the value that you just pushed back, right? So that's a postcondition of pushback. So if that doesn't hold, then there is a bug, again, across an API boundary, right? But now in the other way. So now there is a bug in the implementation of pushback, and that it manifests potentially as UB or in other ways on the caller side, right? So it's another bug across an API boundary, but in the other direction. That's a postcondition. Here's another postcondition of pushback. The size is now size plus 1, right? And so note that pushback might throw, but this postcondition is about when it returns. If it doesn't return, if it throws, there's a different set of postconditions, which I'm not going to write down here. And we kind of have to do this odd thing here now. We can say, well, at the beginning of the function, we have to kind of remember this old size. And then we check the predicate when the function returns. So there is really no good way to express this with a macro, right? Because we have to do something in the beginning and something in the end. And maybe you can kind of hack something, but it's not typically possible to express this like in a general way where it kind of always works. And then there's another type of postcondition which talks about the return value. And so pushback actually doesn't have a return value, it returns void. Like I really think it should actually return a reference to the element that it just pushed back, and that would be nice if it could do that. We can't actually add that to the standard because that would be an API break. So we can't do that, but you can do that in your own library, right? So pushback could return a reference to the element that it just pushed back. And then we can formulate a postcondition, that return value actually is exactly that object in memory that's now at the end of the vector. But again, we can't really implement this as a macro today because there's no way to like name the return value of the function, right? So that's a bit unfortunate. And then the last contract kind is a class invariant, and it would be really nice to be able to write, for example, if we have like some kind of vector and it's an invariant of this class that the vector is always sorted, to just write that in code, right? This vector is always sorted. And we can't do that with macros either today, but let me just kind of observe that an invariant can be expressed with pre and post conditions, right? So if you have an invariant like this, then it's always going to be a post condition of the constructor because the constructor establishes the class invariant. It's going to be a precondition of the destructor, and it's going to be both a pre and a post condition of every public member function. So we can express it like this. We can't really implement it without language support today. So this is what we can do today, which is actually pretty good, right? We can support all the contract semantics that we want. We can support at least preconditions and assertions, which is already super, super useful. And we can support custom violation handling, right? We can handle the contract failure in whatever way we want. So actually, there's a lot of stuff that we can use today in our code, to program with contracts. So then the next question, of course, is, are there some best practices, how do we write good contracts? How do we add contracts to our code? Maybe you're already doing this, right? Kind of implicitly by writing these assertions. Maybe we don't know that they're contracts. Maybe we do. But what are good practices, about adding contracts? And this is something that I could spend the rest of my talk talking about. I don't actually have to do that because this talk already exists. So it's another talk that I highly recommend by Rostislav Khlebnikov. This is a talk that he gave at ACCU this year about exactly this. How to write good contracts, what are good practices. I don't think the video is out yet, but I'm pretty sure, given that the conference was in April, that the video is going to be out on YouTube probably within the next 2 weeks. That's kind of my guess. This is usually how long it takes there. So I recommend you check this out. There's a lot of takeaways I had from this talk. I thought it was a great talk. Kind of the main takeaway for me was, that you should write the preconditions and postconditions first, before you actually implement the function, because it kind of forces you to think about, what contracts do you want to establish for your function. So that got me thinking, okay, so this seems to be a really good practice, but there is something else which we do, which is kind of a good idea to do that before you actually implement the function, which helps find bugs. What's that? Yes, writing unit tests. Right. So writing unit tests is great. I hope I don't have to sell to you that unit tests are great. But I heard a few people saying, well, unit testing and contracts, don't they kind of solve the same problem? Don't they kind of overlap? Is that not kind of ish, the same thing-ish? And actually, no, they're not. They have things in common, but actually they kind of complement each other. Right? You kind of need both, really. You need contracts and contract checks, and you need unit testing. It's kind of like with this kind of testing pyramid where you have like slices of cheese, right? And like different slices of cheese have like different holes in different places, and like, one strategy to find bugs is going to find some of them, but it has some holes, and then the next layer also has some holes, but maybe it has holes in a different place, right? So it's like this, right? Writing tests and writing contract checks is like two different slices of cheese here. So let's talk about unit testing. I actually, when I first found out about unit testing, it really changed kind of the way I program. Ever since then, I have this setup, which even if I write some toy code, just like little example, I always have this setup where I have like the kind of testing framework on the left, and I have the code on the right. And I can't really write code any other way. If I don't have the testing thing on the left, I feel kind of naked. I'm like, well, I don't know if my code is actually doing the thing that I wanted to do. How can I program this way, right? So I always have this thing where I have to write a test, and I write the code that makes the test pass, and it's green, and I write a new test, and I write more code, and it's great, right? It's very satisfying. It's a lot of fun. I find a lot of bugs this way that would be a lot more expensive to find later. I end up with code that looks good, that's well designed. I actually understand my code a lot better. So I hope I don't have to sell unit testing to you. Unit testing is great. So let's do some unit testing here. Let's write a test case for our vector front function that we already saw a few times that we want to implement. Right? So okay, I always start with a test case, and then okay, I want vector front. I want to test it. So what does it do? It returns the first element of a vector. Okay, so let's have a vector and call vector front, and it should return the first element. Okay, so that's my first test case. Of course, that doesn't compile because I haven't written front yet, right? So I'm gonna add a dummy implementation, and now it compiles. The test, of course, fails. Now I implement it, and now the test passes, and everything's great, right? So this is how I like coding. This is fun. But we just learned that before implementing a function, we should actually think about our contracts, right? So we should think about pre and post conditions. So what I want to do now is I want to write my assert here, right? The precondition check. And that kind of forces me to think, okay, what do I want to happen here actually? How am I going to design this class? If somebody calls front on an empty vector, is this going to throw an exception? Is this going to be UB? It forces me to think about that before I implement stuff, right? So that's really good. So here I decided, okay, it's going to be UB, right? So I write my precondition check here. And then I implement the function. Okay, so that's great. But it turns out this line of code here, right, it's a really, really, really important line of code. If you don't write that line of code, then precondition check is not going to be there. And somebody else might take your library, call front out of contract, not realize that, cause hard UB, nasty bugs. No, you don't want that. So you want that line of code to be there. It's a very, very important line of code. And so what do we do with important lines of code? We need to make sure that they're there. So we need to test them, right? So that's very important. And this, for a reason that I really cannot comprehend, seems to be somehow controversial. Like, I heard people say, well, but you're testing your tests, and we don't do that because then we end up testing the test, and it's turtles all the way down, and this is not what we do. Or unit testing, it's not about, like, we don't consider things that are UB. This is not what unit testing is about. These people are wrong. Testing your preconditions is really important because your precondition check is a really important line of code. It's really important to make sure that you wrote it and that you wrote it correctly also, right? That you wrote the correct check there, right? And in order to make that sure that you did, you write a test to make sure that you did. And this way, you're going to prevent bugs, right? Because other people are not going to call your function out of contract without realizing it, and they're not going to cause other bugs. So this testing of preconditions really helps, reduce real bugs, right? So it's kind of like this thing. Like, I think about testing like double entry bookkeeping, right? Where you have like debit, credit, right? And then if you know that everything adds up, you have like both sides, then you know that your accounts are done correctly, right? So we should do the same thing here. And so the next question, of course, is how do we test our preconditions? Well, I do the same thing I always do. I start with a test case, right? And then I want to test an empty vector. So I have an empty vector and I want to test that, vector front causes, a precondition violation. So I can come up with some kind of macro, right, that says require assert fail. And then if that assert fires, then the require assert fail macro is going to check if that assert fires. How do we implement that macro? So, well, the problem here is that we can't, like, once the assert has fired, we can't just keep going, right? Because then we're going to hit hard UB. We can't do that. So we need a way to get out of this function front and back to the unit testing framework without returning a value. Is there a mechanism in C++ that lets us do that? Exceptions, that's it, exactly. So we can implement this macro by saying, well, if you're in test assertions mode, the assertion is going to check our precondition, and if that's violated, you're going to throw an assert fail. And then, we can put, whatever information we want about like where it happened and how it happened, like into that exception class because it's our own class. I'm not going to write that here because it's slideware, but we can do all of that, right? And then we can implement our require assert fail as a simple require throws, which is going to check that, the right exception type has been thrown. And every C++ unit testing framework I've ever seen is going to give you a macro like that. So it's actually dead easy to implement this, right? It's like really, really easy to go into your code and implement tests for your precondition checks. It gets rid of lots of bugs and it's really, really easy to do. Right, so we end up with this. Of course, there's one teeny tiny problem. So you might observe that all front really does is it returns a reference to an element in an array. That can never throw an exception if you just look at the kind of implementation, right? So some people would then argue, well, if it never throws an exception, we should mark it Noexcept, right? Well, now we have a problem, right? That's not good. That's completely destroys our testing strategy here. That's not good. So there is a rule saying don't do that. It's called the Lakers rule. We had it in the standard for quite a while now. It says that if you have a function with an error contract, don't declare it Noexcept, even if you know that it will never throw when called in contract. Instead, document that it does not throw. And this is what the standard library does, right? We have this all over the place. Whenever we have a precondition, the function might still throw, but if we know that it's never going to throw, standard is going to say throws nothing, like operate a square bracket or front, throws nothing. Note that there is no Noexcept there. And so there's multiple reasons why you want to do that. One is that it does enable the strategy of testing preconditions. Another really important reason, which has nothing to do with testing, is that it actually enables widening the contract later without breaking code, right? So if you have this implementation, let's say in version 1, you say, calling front on an empty, let's say this is not standard vector, this is like your own code, right? And so you can say in version 1, it's UB to call front on an empty vector. But then in version 2, I want to make it safer, and I want to say, well, now it's going to be a wide contract, and it's now going to throw some exception, if you do that, right? And so if you do it like this, it's kind of the right-hand side is Liskov substitutable for the left-hand side, right? So you're never going to break code if you do this kind of widening of the contract. But if you have a Noexcept there, that's no longer the case, right? Now, throwing an exception, widening the contract can be a breaking change, right? Because there might be code relying on that Noexcept being there, right? So that's no longer Liskov substitutable for the left bit. And so once I discovered this, I was like, so clearly this Noexcept doesn't belong here. But I have always been happily sprinkling Noexcept all over my code for all of these years. So maybe I didn't actually understand what Noexcept was for, right? So what is actually the purpose of Noexcept? It was actually quite interesting because I was asking myself that question after having used that feature for many, many years. And so it turns out that the purpose of Noexcept as it was designed and the reason it was added to the standard is to do this and exactly this, right? So if you have a situation like vector pushback and you need to satisfy the strong exception guarantee, you have this Noexcept operator, right? And if something's marked Noexcept, you can switch on that operator to select the right algorithm. You can say, well, if the move constructor is not marked Noexcept, then I'm gonna go kind of the slow path because then I need to undo things later and I'm gonna copy them rather than moving them. But if the move constructor is Noexcept, then I can go the fast path, right? So that's only really relevant for move constructors and maybe for copy constructors and swap. But that really is that is why we have Noexcept in the language, okay? And so this kind of has a long history here. So this problem was first discovered, while C++11 and move semantics were actually developed. So Douglas Gregor and David Abrahams published a paper in 2009 saying, oh, this is a problem. Then a year later, they came up with a solution. Okay, for these cases, let's have this Noexcept thing, and let's have a Noexcept operator, and then we can query that, right? And so then another year later, Alistair and John Lakos discovered that, well, Noexcept actually prevents this kind of testing that we were just doing, right? And so then, they established this rule that, we shouldn't do that. The Lakos rule says we should not put Noexcept on functions with a narrow contract. And so that was kind of agreed that this is going to be the policy, at least for the standard library. There was another paper by Nico in 2018, kind of updating the wording of that rule a little bit. And then 2 years later, there was another paper kind of saying, well, but it's kind of weird that we have throws nothing and Noexcept and why are these two different things? They should really be the same thing, kind of disregarding all of this other stuff. And so then, LEWG, which is like the library design group, apparently voted that they're going to follow this new guideline of not doing the Lakos rule. So that's a problem, right? So then I published a paper with Ed Catmuir saying, well, but you can't do that because we're not going to be able to test our preconditions anymore. And then John Lakos published another paper saying, you can't do that because it breaks Liskov substitution and the kind of backwards compatibility thing. And so that's all kind of ongoing. I'm gonna have some kind of showdown at the next committee meeting in Kona. I mean, I know what the right answer is, but let's see if we get there. So, and I know that because I discovered it the painful way, right? It turns out that there are really no good alternatives, right? So I was in exactly this situation. I was writing preconditions for my code. That was in a real code base doing music software, right? And then we had this engineer on the team, the algorithm engineer, they really care about performance, and he was sprinkling Noexcept all over the code and saying that somehow this makes his code faster, even though he could not actually present any benchmarks proving that. And that wouldn't let me write the test that I wanted to write. And so I was like, how do I work around this? And so I took a really deep dive. I looked into like all the possible ways I could think of to kind of circumvent that. And I actually wrote this all up in this paper. So the first thing that I thought of, okay, well, if you can't do Noexcept, so then maybe we can wrap Noexcept in a macro. And if you're testing our assertions, then we're not going to have Noexcept. But if you're not testing our assertions, we are going to have Noexcept. And then we have to slap this macro on these functions, right? And it seemed like a good idea at the time. Turned out I was not the only person who thought of doing that. libc++, actually, the client implementation of the standard library, went through exactly the same pain at some point. They were facing the same thing. They wanted to add tests for their preconditions. They had Noexcept all over the place. Couldn't get rid of it because of backwards compatibility. People were relying on things being Noexcept. So they introduced this Noexcept debug macro, which was doing exactly what I just showed. And this is from like the kind of pull request. And I just love this last paragraph. It says, having thought more and having grown wiser, this macro was a horrible decision. It was viral, it didn't cover all the cases it needed to, and was observable to the user. It was changing the behavior of the program. Well, this is a bad idea. So what do we do, right? So we need to somehow, like, if we hit this assert, get out of the function without returning, but also without throwing an exception. How do we do that? And I spent a lot of time trying to figure this out. And there are a few alternatives, but they all suck. They really do. I went through this in like quite excruciating detail. You can read it in this paper, 2831, I think is the paper number. So I first look at set jump, long jump, right? If you can't throw an exception, you can long jump out of it, right? Well, no. So you can, but if you have any kind of object there with a non-trivial destructor, and like stack unwinding would have called that destructor, but it's not being called because you're doing long jump instead, that's actually blanket UB. You just can't do that. So that's not an option. So another thing that I thought of, okay, you could like start the test in like a child thread, right? And then you can, if the assert fails, you can like save the info about what happened and then like somehow put the thread to sleep indefinitely or like let it spin indefinitely or something like this so that the thread is kind of not doing anything anymore. It's never going to hit that UB, which kind of doesn't work, right? Because it leaks memory. It invalidates anything that relies on error because the stack is never going to be unwound. And maybe that's the thing you're actually testing, right? So this just really doesn't work. It also leaks one thread per test case, which is not good if you have 10,000 test cases. So there's another approach that Ville Voutilainen came up with on the committee mailing list, which is kind of similar to stackful coroutines, kind of implemented by hand. So what you can do is you can, when you hit your assert fail, instead of returning anywhere, you can just call the event loop of the test framework, and that's just going to call the next test. And when that fails, it's going to call the event loop of the testing framework, and it's going to call the next test, right? So the other tests, they're kind of never continuing because they're like further down the call stack. So yes, but like it has all of the same problems, like it leaks memory, RI doesn't work. Your call stack also keeps growing with every test, so you're going to hit a stack overflow at some point. It's kind of difficult to put together. Like Ville showed like a toy implementation, but I don't know of anybody actually doing this in production, so it's actually not really, it's not really a viable approach. The next thing that somebody suggested was, why don't you use signals? Well, yeah, we can like, if the assert fails, we can like raise a signal and then we can have a custom signal handler. But that's just a callback mechanism, right? So now we're in a signal handler. We have the same problem. We have to return somewhere, right? So that just shifts the problem one level higher. And anything based on callbacks is not going to solve this problem of actually having to leave the function and go back to the testing framework. And so the only alternative that actually kind of works is something called death tests. That's really the only like viable, and for some definition of viable alternative to like the Lakers rule and doing this with exceptions. And there's like 3 flavors of this. You have fork-based, clone-based, and spawn-based death tests. So fork-based basically means you launch each test in a forked process, right? And then when you hit the assert, it terminates that process, right? And so, yeah, you can do that on a platform if you have like a really fast fork. So that already means it's only on Unix platforms, right? It's going to be much slower on Windows, and if you're like on something like embedded where you don't even have processes, then this just doesn't work at all. Like if you exit a process, you only have 8 bits of data. I mean, you can establish like a side channel to do this, but then it's just a lot of mechanics you have to set up, right? And so it's so complicated to do this that actually no unit testing framework for C++ that I know of, except Google Test, actually offers that. So if for some reason you can't use Google Test, like for example, in the company where this was happening at the time, we were using catch. And so we were like, okay, we need to add death tests to catch somehow. And we looked into it. This was so complicated. If you're like, at the time, you were like a startup, we didn't have time to do this, right? So it was basically infeasible for us to do this. So then you just end up not writing check tests for your preconditions. You end up like risking all of these bugs, right? So you can do fork-based, you can do clone-based, which is a bit more stable than fork-based, but it's Linux only. And then the last one is spawn-based, which is even more complicated to set up. Like you spawn a new process every time, right? So that requires that the test in a separate file. It's actually really slow, like on every platform, including Unix platforms. And that's actually really bad, right? Because it's going to turn your test suite potentially from something that runs in 3 seconds to something that runs in 10 minutes. And then you're not going to run your whole test suite every time, right? And so what's the point of test suite then, right? So this really doesn't work. So the kind of the takeaways from this exercise, write your pre and post conditions before implementing the function. Test your preconditions. And the best way to do this is to do exception-based precondition testing, because it actually works. On every platform that supports exceptions, it's easy, it's efficient, it's scalable, it's fast. You have to follow the Lakers rule if you want to do that. And kind of as a general recommendation, you should do is Noexcept maybe sparingly. Like if you really want your code to check the thing that you wrote with a Noexcept operator, then you put Noexcept there. Otherwise, probably you don't need it. And apparently that is also something that's controversial, because people are saying, well, we annotate things with throws nothing, but we don't mark them Noexcept, and we lose out on optimizations, right? So because Noexcept gives us better code gen, right? There's a question.
Yeah, did you take a try instead expected?
Well, so that changes the signature of the function, right? So then the return type changes. So then kind of it creeps into like the production version of it. You can't just remove it, right? So we can talk about this later. There's another hand. I have, I think, 15 minutes left or something. So let's do this. Let's do this afterwards. I don't want to like get into like a rabbit hole. This is a fascinating discussion, but let's have it afterwards. Noexcept, does change code gen. Matt Godbold is nodding. So that's a good sign. So if you have a function g, which is Noexcept, and it's called a function f that is not Noexcept, effectively the compiler has to generate something like this, right? But if you mark f as Noexcept, that code goes away, so you're going to get more compact code gen. Also, if everything is Noexcept, you don't have to, compiler doesn't have to generate unwinding info, so your binary is going to be smaller. So, there are some benefits. I would argue that if you really care about binary size that much, you probably don't use exceptions in the first place. So I don't really know who's affected by this, that much, that they really have to sprinkle Noexcept all over their code base. But maybe those use cases exist. I'm curious to hear about them. But also, like every time somebody says, yes, but I want to put Noexcept there, they were claiming that it makes their code faster. I was like, show me a benchmark. And I haven't seen any such benchmarks yet. I haven't seen any proof that Noexcept makes any actual real-world code faster, or removing it makes it slower. Right? I haven't seen that benchmark. I asked quite a lot of people. I've never seen a benchmark actually proving that. Every benchmark there's no measurable difference on modern platforms. Like obviously there are platforms like Windows 32 where like the unwinding is done at runtime. That's like a different thing. But like on modern platforms, there's no difference. There's no measurable difference that is not distinguishable from like cache line noise, basically. But, there's this argument like kind of we want to have this different code gen, and we don't want to choose between that and, using preconditions. So maybe there is a solution that makes everybody happy. And this is an idea that Pablo Halpern came up with at the last committee meeting in Varna. There's now a paper in the next mailing. And so maybe we can solve this by kind of, instead of Noexcept, having a new attribute. throws nothing. And then it's going to do exactly the same thing as Noexcept. Like you get all the same benefits, right? Except with two differences. It's an attribute, so it's optional, so you can turn it off, right? So the compiler can offer some kind of flag that you can turn it off, and then you can use the exception-based precondition testing. And the second difference is that you cannot query it with like the Noexcept operator. And therefore, if you switch it off, it's never going to actually change which code you're executing. And that kind of sort of seems to solve the problem. You know, let's see how far this paper gets in the committee. Maybe somebody has a better idea, but I think this is an interesting way forward. And now that we're speaking about like things that are happening on the committee, there's, of course, you know, the big thing that's happening right now, which is we're actually trying to standardize contracts so you all can use them. So here's the slide again. You know, a C++ contract facility should be able to do all of those things. It should support the 4 possible contract semantics, the checked ones, enforce, observe, the unchecked ones, ignore, assume. It should support preconditions, postconditions, assertions. Invariants, yes, we're actually not quite sure how to do them. Like there's quite a few complications with this. So there's currently no paper like proposing invariants. So this is something for later. It seems to be like a kind of a difficult problem how to like actually do this. You want to support custom violation handling. And we can do all of those things, you know, including postconditions. If you have this as a standard language feature, right? Not library, as a language feature. But you can do so much more if it's a language feature, right? So we can use contracts as input for static analysis, for formula verification, all of these other things. This is what, you know, contracts were designed for in the 80s, like for, you know, if you have languages like Eiffel or Ada, like you can use contracts for this kind of stuff, right? Which actually addresses not just safety, but also correctness, you know, in very, very interesting ways. If you have standard contracts, you can make them accessible to other tools like IDEs. How cool would it be if your IDE would understand your contracts, right? And the most important one, we can make contracts usable scalably across libraries and across API boundaries. Like right now, you might have the best assume macro in the world, but it's for your library, and the other library is going to have a different assert macro, right? And so they can't talk to each other. But if it's in a standard, everybody agrees on what they look like and how to, you know, handle violations of these contracts, then we can do this across our whole code base, right? Including third-party libraries and everything. And how awesome would that be, right? So standardizing contracts goes back in C++, actually goes back quite a while. There were kind of three acts to this, like 3 waves, right? So the first wave, this is like the earliest paper I could find. There was a proposal all the way back in 2004 to add contracts to C++, and it was a proper proposal. It had syntax and everything. And then this is kind of the last revision of this particular proposal was from 2006. I'm not quite sure why exactly the committee didn't end up standardizing it then. But there is a paper kind of from this wave, like the last one that I could find is 2015. And that one has a huge amount of references about kind of all the stuff that happened in between. So this is like a really, really good reference about like this whole first wave of like trying to get contracts into C++ and what that means and how that would work. Then there was a second act, which is this paper, this proposal by Gabriel Dos Reis, Jose Daniel, John Lakos, Alistair, Nathan, and Bjarne, who actually put a lot of effort into writing up a proposal, a complete proposal for adding contracts to C++20. And that was actually reviewed by the committee. We had consensus for this proposal. It was actually voted into C++20. It was in a C++20 working draft. And then after that has happened, it turned out that there were quite a few things in this proposal where some authors of this paper thought contracts would work this way, if this happens and that happens. And then some authors of this proposal thought that it would work in this other way. And then the wording that ended up being in the C++20 draft actually said like a third thing. And so as soon as kind of this was discovered, like consensus unraveled, pretty quickly. And then at the meeting in Cologne in 2019, which Peter will remember, which was the last meeting to make changes to C++20, we ended up ripping out the whole thing. And so then after that, we said, okay, we need to like start from scratch. Like we need to sort this out. So here's an org chart of the C++ committee. So we have these 3 levels, right? We have the study groups, which are concerned with particular topics, like this is the green stuff, and then we have the blue ones, which are the design groups, and then we have the brown ones, which are like the last stage, that's like the wording groups. And so we ended up establishing a study group for contracts, SG21, which I am chairing together with John Spicer. And we kind of just said, okay, let's start from scratch. Let's actually figure out, what are contracts actually for? Because it turned out the authors of that proposal, they didn't even agree on that. There were quite a few significant disagreements on what you should use contracts for. So we kind of started over, like, this paper has lots of use cases, and we quickly figured out we can't satisfy all of them. Like, there will not be a proposal that satisfies all of these use cases. So maybe we should focus on, like, the most important ones and get that into C++, and then do kind of the other use cases kind of later as an extension. So it seems like there are use cases that are kind of more important than others. And for me personally, I think that the one most important use case, like if you ask me what contracts are for, this would be my answer. Contracts are for finding bugs, scalably across API boundaries. This is what I think contracts are primarily for. You can do lots of other things with them, like formula verification and all kinds of other stuff. But this is kind of the most important use case for C++ today, in my opinion, because this is going to give the most benefit for us writing day-to-day code. So what you're working on in SG21 is to standardize what we call a contracts MVP, minimal viable product, kind of like a small subset of what we could possibly do that satisfies this really important use case, right? And we're actually targeting C++26 with this. And so, there is this paper here, which is kind of a roadmap, where, if you want to get this in C++26, there are certain deadlines, right? There's a certain feature freeze date, so you kind of work back from that, and certain things need to happen at a certain time for that to happen. We're kind of currently here, so I feel pretty positive about this. We have plenty of time to get this done. And so I want to spend a few minutes talking about, how this contracts MVP would actually look and what it would do. So let's say we have a function. So with C++26 contracts, if everything goes well, which I'm fairly confident it will, we will be able to add a precondition, add a postcondition, and now we can introduce a name like R here to refer to the return value directly of that function. And note that these are now on the declaration of the function. These are not asserts in the function body. These are on the declaration of the function, right? So that's really, really important. So we can refer to the return value here. And then we also will have assertions, which you can put in the function body. And they will basically be a drop-in replacement for CAssert, except better and more flexible. So this is kind of the basic feature, right? So we have preconditions, postconditions, and assertions. We also have different contract semantics. So these are the four. We quickly figured out that assume is kind of nice for performance if you know what you're doing. It's a kind of an expert level feature. There's a lot you can go wrong. So it's kind of like juggling razor blades, as we saw earlier. And B, it doesn't really address this kind of MVP use case of finding bugs. Assume is not going to help you finding bugs. It's going to help you introduce bugs if you don't know what you're doing. It's like reinterpret cast or something like this, right? So we decided not to do this for the MVP and focus on enforce, observe, and ignore. And so then there was another thing in the original C++20 contracts proposal where it had build modes, and it said there's this standard build mode and this build mode and this build mode, and then if you put this label on your contract check, then it's going to map to this semantic and this build mode and to this semantic and that build mode. And it felt like this was kind of overly specific and a little bit over-engineered maybe. And so we decided to scale it down, and so there was a proposal for the MVP to just have two build modes saying all contracts are ignore. That's the no eval build mode. Or all contracts are enforce. That's the eval and abort build mode. But we quickly figured out that that's actually not a good approach either, because actually standardizing build modes is actually maybe not a good idea in itself, right? Because then, if you say you have to have different build modes, if you want to be conformant compiler, there's all of these questions. What if you're a package manager? Do you need to now ship 2 binaries instead of 1? What if you're shipping debug release? Do you now ship 4? Is this like a combinatorial explosion of binaries if you have all these different build modes? And what happens if you want to switch to semantic maybe at link time or even at runtime if you're like a C++ interpreter, right? So we kind of got rid of build modes. This is like the latest paper on the subject that we have consensus for that we voted in. So it now says that, oh, and the other thing is that we kind of really wanted this observe mode because it is useful occasionally, right? So in the MVP right now, we have all of these 3 semantics, enforce, observe, ignore. And we say it's implementation defined which one you get. So it's kind of like depending on the compiler, the ecosystem, like you can do whatever makes sense, for that platform and still be conformant, right? So for example, if you're a C++ interpreter, you can switch the semantic at runtime, you can still be conformant. There was a recommendation that there should be a build mode where all contracts are enforced and a build mode where all contracts are ignored. And there's another recommendation that the enforce is going to should be the default, so it's exactly like C assert in that sense. But those are not required, right? So we leave the kind of space open for the ecosystem to figure out what the best way is to do this. And so then the other thing, kind of the last piece of the puzzle that you need is a violation handler. So there is a standard violation handler, which is just going to basically print a diagnostic and that's it. But you can write your own. And it's going to be a replaceable function like operator new, operator delete. So you can define it yourself and you can link it in. It's very important that you cannot switch it at runtime because that would be kind of a security issue. You can define your own violation handler. In there you can do whatever you want. You get this one parameter, the violation object. So you're gonna get that basically from the compiler that has all the obvious members, right? It's gonna tell you where did the contract violation occur. Comment says like what was the expression, detection mode, like what did actually happen? Did the contract evaluate to false or did it throw or something else? What was the semantic? What is a semantic? Is it observe? Is it enforce? And what's the contract kind? Is it a precondition? Is it a postcondition? Is it an assertion? So you have all of this information, and then you can do your own violation handling. You can log. You can set a breakpoint. Hopefully soon in the standard version in CppNorth23. Thanks, Renee. And you can also throw an exception. That's going to enable the precondition testing that we saw earlier, right? So you can do that. You still need to follow the Lakos rule because we decided we don't want to circumvent the Noexcept operator somehow. We don't want to have something that's declared Noexcept, but then all of a sudden it can throw. That would be really weird. It would probably break a lot of stuff. So if you have a function that's kind of marked Noexcept, and then you throw from the violation handler, you're still going to slam into that Noexcept, and it's going to be a terminate, right? So you have to follow the Lakos rule and not put Noexcept there if you want to use this technique, for example, for testing preconditions. And yeah, that's pretty much all there is. That's it. That's like our contracts MVP. And I think that's very, very useful, certainly a lot better than we have today. And when we have that, like this whole machinery with like violation handling and like the contract semantics, that is super powerful, right? So once we have the contracts MVP, we keep going, we can contract all the things, right? We can, actually, it's really cool. You can look at so many things that are happening in C++, and it's actually a contract, or it's like something that has a contract. It's everywhere. Like once you think in that way, you see contracts everywhere. Let me give you a few examples. Noexcept. We talked about Noexcept quite a lot. Turns out Noexcept is actually a contract, right? It's a postcondition that F is not going to throw. Except that the semantic of that contract is kind of hardwired, right? It's always in force. So it's always going to terminate if it's violated. Wouldn't it be cool if you could make that configurable, right? You can say, well, maybe you want the semantic to be assumed, and then you can get even better optimizations and even better code gen due to Noexcept, right? And that really applies to almost everything in C++. Specifically, everything where you have UB, also hard UB, like hard language UB, all of the stuff that we were talking about in the beginning. Let's give you an example. Signed integer addition, built-in operator plus for signed integers. That has a precondition. The precondition is that it's not going to overflow, right? And the semantic of that is hardwired to be always assumed, right? Like always optimized based on the assumption that this never happens. Wouldn't it be cool if that would be configurable? If you could say, well, but I have this, big mathematical simulation, like it's giving me really weird numbers, but like I don't want to throw like a sanitizer on it. That's going to be way too slow. I just want to flip this one switch in my compiler, without any extra tools, and say, well, it should be observed and it should just log whenever that happens. And you find the bugs this way. Wouldn't that be amazing if you could just do that with a C++ compiler out of the box? And this is the world I want to live in, and I really hope we're gonna get there. Of course, before we get there, we need to actually standardize the contracts MVP first. And in order to get there, we need to slay one final boss. And I know I'm 2 minutes over, but this is like the very last section, the syntax. You don't actually agree on the syntax yet. So there is the syntax from the CppNorth23 proposal, which looks like this. And it's great, right? Because you have these delimiters, these like double square brackets, which are going to clearly separate the contract notation from the rest of the code. It has lots of benefits, like you're not going to run into any parsing ambiguities. You can, like, it's very open for extensions, like you can put like labels in there, like kind of later, do all kinds of interesting stuff. And also we have implementation experience, like this has been implemented in GCC, right? You can use this today, right? So we know this works. I think it's also on Compile Explorer, Matt, isn't it? I'm pretty sure that branch of GCC is somewhere in Compile Explorer, so you can play around with this today. But some people say, well, these double square brackets, they're kind of ugly. It's kind of a very heavy syntax. I don't like the way this looks. And also it looks like attributes, but contracts are actually not attributes. They're not ignorable. Maybe they are, depending on how you define what ignorable means. And it's kind of very confusing. People don't like that. So there was this kind of counter proposal, which says, well, let's spell it like this. You know, so with curly braces. And that's actually quite nice. And that proposal also proposed another syntax that lets you do something really cool. So if you have these curly braces, you can actually write captures, the way you write captures for lambdas, right? You can say, well, you have a postcondition, you can kind of capture a value when you enter the function. And then you can use that capture, you know, when you check the postcondition at the end of the function. That's really cool, right? You can do stuff like this. There's one problem with this syntax as well. This is actually an expression, right? So it's like kind of an expression that returns bool, right? So normally in C++, we put statements in curly braces, like the body of a function, and then you put expressions into parens. But now we have an expression in curly, so that's kind of really odd. There was a third proposal, you know, let's put the expression into parens like we do for if condition or while condition. Let's say, okay, precondition, right? But that kind of, yeah, that also has problems. You might run into like some parsing ambiguities if you do kind of certain stuff with this. It's totally unclear how to do the capture thing. Actually, that's unclear in both of the syntaxes. Like with the first one, it's probably going to be ugly if you have like nested square brackets. We don't really know how to do this. With the second one, we don't know how to do this. We don't even know how to refer to to the return value with the syntax. And the proposal originally said, let's have a predefined identifier that just says result, and that's going to be the return value, but I actually really don't like this. Like imagine you have a complicated expression, you have to like write 3 times, result times result times result. I don't like this. So we have this paper now, which kind of goes through all the different trade-offs and like this syntax can do this better, this syntax can do this better. So if you're interested or if you have ideas, you can obviously talk to me, but you can also read this paper. All the gory details, a 25-page document. So at the next committee meeting in Kona, we need to somehow figure this out and kind of decide on a syntax. But I'm actually quite confident that we're going to get there. We have you know, a couple other things that we need to figure out, kind of minor things like how do contracts interact with virtual functions? What do contracts do, you know, during constant evaluation, like in const expo land? We kind of haven't quite figured out these details yet. But I feel fairly confident that we're going to get there in time for CppNorth26. And then you will be able to use contracts in CppNorth26. And then you will be able to use them scalably across libraries, across API boundaries, to write safer code with less undefined behavior. Thank you.